Hello. By this time, you should have looked at a video talking about light that can act as a particle and light that can act as a wave, and how you can figure out the calculations associated with each one of them individually. This is a discussion on how we're going to use them together in how it relates to the atom. Well, Max Planck and the people who believe that light was a particle feel that when the light comes at you, it comes at you in packet sizes. Therefore, that's how he gets his frequencies related to energy equation. Uh, the people who believe it's a wave feel it has the wave characteristics of frequency and wavelength. De Broglie said they're actually both at the same time. So therefore, what you can do is you can bring the two equations together, and you can use the frequency and the wavelength equation and to find out the energy in the energy equations. So therefore, you can use the frequency from the wave equations in the energy equations. If not, then you wouldn't if you didn't have de Broglie's duality of light, you wouldn't be able to do that because it wouldn't make physical sense. Um, why do we want to do that at all? Well, if you remember back when we talked about Bohr's model, what Bohr said was the electrons couldn't be any distance away from the nucleus. They had to be in discrete distance away, called energy levels. And the distances away from the nucleus of the electron was proportional to the energy that the electron had. Furthermore, he said that energy and atoms relate as the following: that the atom, as long as it's not absorbing energy and emitting energy, all the electrons are in the lowest energy level possible, available, um, and the electrons are revolving around the nucleus like planets around the sun in those energy levels, almost like the electrons are sitting on the skins of an onion, not in between. And it's called the ground state. And when energy comes at the atom, as Planck would say, it comes in energy packet sizes. And what the atom will do is the atom will only absorb that specific packet size so that an electron in a lower energy level can promote or jump to a higher energy level. And it's only that specific amount of energy, because remember that's a specific distance and they're basically equal to each other, so that atom only absorbs specific energy packet sizes. And when it does, an electron is in a higher energy level, the atom is said to be in the excited state. The atom will instantaneously allow the electron to fall back down to the lower energy level, making the atom back into the ground state. And when it does it, it releases that exact packet of energy and it's being emitted. And we only see the emission. And it's emitted, of course, as an energy, which is a frequency, which is a wavelength. And if the wavelength is the right wavelength, in our case, we like to look at use the numbers in the nanometers, then it could be what we call color. So that set of manipulations is our mathematical manipulations. So that's why we want to be able to do the calculations, because we could then determine the color, or the wavelength more correctly in nanometers, that the atom is emitting, absorbing first but then emitting. Uh, the interesting thing about atoms are they all have the same number of electrons, so therefore they have all the same number of electrons in the different energy levels, so they will absorb the same sets of specific energy packet sizes. So every single atom of the same type absorbs and emits the same exact energy packets. So this is called a bright line spectra, and we'll be able to talk about that a little bit more. But it's a way of determining, or a way of seeing an element or differentiate elements from other elements. So let's get to, and we're going to be doing that in the lab, what's called the flame test lab, and there'll be a video on that too. So let's get to the equations, and that's really why we're doing this, is because now we can indicate what element is present by the absorption / emissions of energies due to the as the electron moves around. Okay, so now here's the calculations. So in this case, what we have is we are looking for the wavelength, because the reason why we're looking for the wavelength in nanometers is because our color indicator is in wavelengths in nanometers. So it's kind of like a cheat sheet is in wavelengths in nanometers. And then from that we get the color, which you'll be able to get in class sometime. So in this case, we have energy at 3.46 times 10 to the minus 19th joules. Again, we're given that information, and in this case, we have actually this is a two-step math problem. So therefore, dimensional analysis, you're going to have a couple more brackets. You're going to use Planck's constant, and you're going to use the speed of light with meters times hertz. So again, anytime you use the speed of light with meters times hertz, you need to start off with the first 1 unit thing, because that's what we're looking for, is a 1 unit thing. It needs to be on the bottom. So that's where you put the 3.46 times 10 to the minus 19th joule on the bottom. Then you use Planck's constant with the joule and joules on the top and hertz on the bottom, so we cancel the joules. And the hertz needs to be on the bottoms, because then you're going to use the speed of light with the units meters times hertz, so the hertz cancel, and then you get it in the wavelength in meters. Again, the reason why we need it in nanometers is because that's how our scale, our color scale is. So we're going to go from meters to nanometers, and we end up with 572.2 nanometers, which is 572 nanometers. And then what you would do is you take the 572 nanometers, go to your color chart, and say, oh, it is this color, because that's approximately what you're reading. Okay. By equation, this is a type of two equation question, and you figure out that with the information you provided, you have to solve the energy equation first for frequency. So therefore, you get frequency is equal to energy over hertz. The units will cancel the way you want, so you don't have to do any unit cancellation of the joules first. And you get hertz, which is 5.242 times 10 to the 14th. And in this number here, you want one more significant figure than you need in the answer. And since these are these equations, you're going to always have 3. Okay, and as you can see in the question, there's only 3 significant. The number in the question has only 3 significant figures. So you're going to keep 4 in this one, because it's not the end equation. This is another equation you're going to use. So that frequency you're going to use, and the speed of light you're going to use use in the light equation. So you're going to manipulate the light equation to give you wavelength is equal to c over f. You plug those in. The hertz will cancel, and you get meters. And again, you want it in nanometers because of our color indicator. So you're going to change the meters to nanometers. You're going to end up with 572.3 nanometers, which is equal to 572 nanometers. And then you use the color chart to get the color. They are both the same exact answer, and that's how you get your answer. And what that answer is telling you is that if your electron absorbs, then emits 3.46 times 10 to the minus 19th joules, your wavelength that you're going to see as a human will be 572 nanometers, and that actually is within the visible spectra. I don't know what color it is, but it's I know it's with. So you're going to see a color, whatever color that is, and that's how you would be able to tell if it's that particular element. Okay, and again, we're going to be doing what's called the flame test lab on this. So that's those are the types of calculations you're going to do. Again, like it just said, the reason why you do it is because this is how atoms absorb energy in pulses, okay, with specific energy amounts. And we see them when they're being emitted as colors or as other wavelengths. We can't see other wavelengths, but we can determine them using instruments. Okay? And it's one of the ways that we can indicate elements in a sample. Thank you.